having given some motivation on the type of problems that we are trying to solve with eigenvalues and eigenvectors, we are now ready to define what are eigenvectors and what are eigenvalues. And the interesting thing is, to define eigenvalues, I actually first have to start by defining eigenvectors. Recall that a matrix A represents a transformation from R3 to R3. So it takes a sorry, I keep on saying R3, but really what I mean is Rn. So I take some vector x in here, in Rn, and I apply the transformation Ax. So I map x into Ax. Somehow, let's say you take a vector from Rn over here, and on the other side, again, we have Rn. It's just easier if we represent it as if it were two vectors. So if this is x, then let's say this vector is some y equal to Ax, then we map x to some different vector, possibly the same, sometimes different vector Ax. Okay, now there are vectors for every matrix. There are such vectors such that if you start with the vector x in Rn, when you apply the transformation Ax, all you get is the vector maybe longer, let's say like that, could be shorter, maybe the direction can be switched, but bottom line is it lies on the same line as x. So it is in the same direction as x. It could very well be the origin. Remember, all of these arrows start from the origin, no matter what the dimensions of the space is. We assume the geometrical picture that we have in our heads in R3 is sufficient or can be extended and generalized when we think in Rn. So what happens when we apply this transformation Ax is that we get perhaps a longer vector. So we get a vector which is a multiple of the original vector x. This only works if x is an eigenvector. And that is exactly the definition. So I'll write it here. So given a matrix A, the vector x is an eigenvector of A with eigenvalue lambda if A times x equals lambda x. Okay. So the basic definition for eigenvalues and eigenvectors is this one equation. The vector x is what we refer to as an eigenvector. So when we work with an eigenvector, we know that multiplication by A will just make the vector longer or shorter. And by how much longer or shorter, or maybe change direction in the opposite direction, is given by the eigenvalue lambda. Now, there can be, for one lambda, if you have one eigenvector, then you have infinitely many eigenvectors. Any linear combination of eigenvectors will do the trick. But also, so for every lambda, there is at least one such vector, but you may also have multiple linearly independent vectors for one lambda. So we'll see how we will decide on the eigenvectors and how many we have per eigenvalue. But the first thing, let me show you that if x is an eigenvector, then any multiple of x is also an eigenvector. So let's see that. Then any multiple, for example, Cx, is also an eigenvector with the same eigenvalue. So this is very easy to see. If x is an eigenvector of A, it means that AX equals lambda x for some lambda. Now, what about A times CX? Well, since C is a constant, it means it can be flushed out on the left of this multiplication. So this equals C times AX. Now, since AX equals lambda x, we have C times lambda x. Now, I can change the order of C and lambda and write lambda times CX. So what did I do here? I multiplied the vector CX by A, and I got as a result that same vector multiplied by lambda. So this gives us a hint that in fact eigenvectors, eigenvalues sort of respect linear combinations. And again, we are in the area of vector spaces. We can't really escape them. Another perhaps even more important property about eigenvalues and eigenvectors is the following. If x is an eigenvector of A with eigenvalue lambda, then what we have is that x is an eigenvector of A squared with eigenvalue lambda squared. How can we see this? Why is this true? Well, look at what does it mean for x to be an eigenvector of A with eigenvalue lambda. It means that it satisfies the equation AX equals lambda x. Now, how can we get to A squared? Well, A squared x is the same as A times AX, because A times A is A squared. Now I know how to compute A times X. That's simply lambda X. So I have A times lambda X. Since lambda is a constant, it can be flushed at the left. So I have lambda AX. And now my AX is again a lambda X. So actually I get lambda squared X. So this equation demonstrates we have A squared X equals a lambda squared X. It demonstrates that A squared has the same eigenvectors as A, and the eigenvalues get squared. So the eigenvalues are not the same, but they are related. Now this is very promising. Remember that when we defined this problem, our original goal was to talk about what happens when we apply a to the n to some vector. In the case of eigenvectors, an times x is something that can be computed very easily. So this is under the assumption that x is an eigenvector. Then what we have is lambda to the n times x. So we have this if x is an eigenvector of A with eigenvalue lambda. So now the problem that we originally set up, where we have some initial state u naught and we want the end state un, you see that if that initial state is an eigenvector, then applying the matrix A to the n to that vector is something very simple. I don't actually have to know, I don't have to find the matrix A to the n to be able to decide or find out what its action on X is. I know its action on X right away because X is a special vector called an eigenvector. Now, why were we looking at these properties? Well, we were looking at the properties to see how to figure out what lambda and x must be given a matrix A. So the question on how to find eigenvalues and eigenvectors remains. If we have, so how to find lambda and x for a given matrix A. By the way, a matrix A may have various eigenvalues, and each of those eigenvalues will have eigenvectors which are linearly independent of each other. So really, I should say how to find lambdas and x's, eigenvectors x, for a given matrix A. Well, the only hope of figuring this out is the definition. So the definition says that A times x must equal lambda x. Now, bringing lambda x on the left-hand side together with ax gives us 0. 0 is pretty powerful. We know what to do with zeros. In this case, 0 is the zero vector, not a 0 as a scalar. So I see here ax and then lambda x. It means I can factor out x, and I have to factor it on the right-hand side because it multiplies a on the right-hand side. Lambda is not important because lambda is a number, so I could very well write x times lambda if I wanted to. So really, it's a times x that says x has to be factored out on the right-hand side. The question is, what do we have in the parentheses? Well, it's very clear that we have an a, and I know many of you will want to just write a lambda here, but that would be wrong. And the reason is that lambda is a number while a is a matrix. So you cannot subtract a number from a matrix. But what you can do is realize that you always have the identity matrix multiplying in between the lambda and the x, because identity times x is just x. So really, in the parentheses, we have a minus lambda I. Now, this equation tells us a lot about where x is and how to figure out lambda. So the first thing we need to realize is that in order for this to be true, it means that x is in the null space of a minus lambda I. And second thing is that the null space of a minus lambda I should not be 0. It should be bigger than 0. You can say the 0 vector is an eigenvector of every matrix with any eigenvalue. But really, we're interested in non-zero eigenvectors. So we're interested in non-trivial solutions to this problem. So we have this idea that we can find x in the null space of a minus lambda I. So then obviously this is what we want to do. We want to find the null space of a minus lambda I. But how do we figure out what lambda is? Because we can't figure out a minus lambda I without knowing what lambda is. Well, if the null space of a minus lambda I is not 0, that tells us that a minus lambda I is a singular matrix. Now, hopefully you haven't forgotten determinants just yet, but if a matrix is singular, it means that its determinant, right, this is the determinant of a minus lambda I. I know it looks like an absolute value, but when you talk about matrices, that means the determinant. This determinant needs to be 0. You see, when your matrix is n by n, a minus lambda I, the determinant of a minus lambda I, gives you a polynomial of degree n. A polynomial, I should say, in lambda of degree n. So you will have lambda to the n and then lower degrees of lambda showing up in that polynomial, and you're making it equal to 0. So really, the lambdas will be the roots or the solutions to this polynomial being equal to 0. So this is really where we find eigenvalues and eigenvectors. I'm going to write a procedure, and then in the next video, we'll see an example or two. So how to find eigenvalues and eigenvectors? The first step is to solve the determinant a minus lambda I equals 0. So as I said, lambda here, you put it as an unknown. You get a polynomial in lambda, you set it equal to 0, and you're trying to find the roots, or you're trying to find the values of lambda for which this equality is true. So you solve this equation to find lambda 1, lambda 2, all the way to lambda n. Now I say there are n lambdas, but that doesn't mean that they all have to be different. You could have repeated roots in the polynomial, but you cannot have more than n. Then the second step is for each lambda, and to indicate that I'm talking about each different lambda, I'm going to say lambda I, find the null space. Every vector in this null space will be an eigenvector of A with eigenvalue lambda I. So we see that here we actually have an eigenspace. You can refer to this as an eigenspace or subspace of A. It's not the only one, so each lambda gives you an eigenspace. And what it means is that when you apply A onto this eigenspace, you stay in that eigenspace. So A times any vector in here will not necessarily be that same vector, but it will stay inside the space. You will not move out of the space. So you have closure under multiplication by A. And with this, I am going to stop in this video.